on with the next speaker. And I think, again, we will set a contrast with the next speaker. And it's somebody with whom I have personally collaborated for a while, Bert Metten. And I know he's very engaged in the whole Belgium academia industry partnership. So certainly you can also comment on this. But he has very different chemical products, and that will become clear, I think, from his talk. So who is Bert? Bert is Technology Development Manager at Ajinomoto Bio-Pharma Services, and that was formerly, or still is called, Omnichem also. And Bert Metten is an organic chemist, so now we changed to a chemist, PhD by training. He has been a researcher all of his career. He has experience in heterocyclic and macromolecular chemistry from a great place, which is Leuven. I think they rank highest in the world in the industrial implementation of research. I saw statistics, they do very well there, and otherwise applied chemistry, PNG, medicinal chemistry, and for the last decade he also went to process chemistry and technology development within Ajinomoto. And he talks about a classic, that is safety relevant synthesis in flow, diazomethane. I've made that personally, and I really was scared when I made it, when I had 1 liter diazomethane, not pure naturally, but in diethylator next to me. I hated it. I would have loved to have a flow reactor at that point. And he talks about scaling up that and look at the bigger picture. So very interesting, what is the big picture? But please start your talk.
Okay, can you see my screen?
I see it, and I assume everybody sees it.
Okay, great. So and thank you for the nice introduction, Volker. As the title says, I will talk about the use of flow processing and the application in the broadest sense of the word. And I will showcase it with a customer project as an example. And I think you will see a lot of links with the talks of Sebastian and Christian. So first, I will introduce the Ajinomoto Group. This is a genuine global manufacturing company working in all kinds of fields related to health and well-being. It could be on pharmaceuticals, foods, specialty chemicals, and even health and beauty. And many of those fields are related with amino acids or natural products or biorenewable compounds. Within the Ajinomoto Group, we have the Ajinomoto Bio-Pharma Services Group, and this is about 1,200 people spread over several sites located in 4 countries. We produce, on average, more than 2 billion doses a year against many indications. In the US side, we have sites specialized in large molecule manufacturing, fill and finish, high potency, and antibody drug conjugates. The India and the Japanese sites from Ajinomoto Bio-Pharma, they provide small molecule manufacturing, and a large part of several sites also work on oligonucleotides and peptide synthesis, mainly thanks to the AjiPhase technology, allowing large-scale manufacturing of those oligonucleotides and oligopeptides. The Belgian sites, where I work, that hosts the largest small molecule manufacturing capacity and also process research and development, including high-potent API synthesis and continuous flow. All sites have some form of expertise in flow applied on their field, but the Center of Excellence in Flow Chemistry is located in Belgium. Again, here are all the services that Ajinomoto Bio-Pharma provides, but the focus today is on the small molecules manufacturing. For the small molecule manufacturing, we have decades of experience in fields, depicted on the slides here, up to 10,000 liter scale. So being it hydride reduction, for example, borane into that 10,000 liter vessels, or organometallic excitrium reactions at minus 90 degrees in 6,000 cryoreactors. That's something we do. Or oxidations with cheap oxidants like the Cody-Kim reaction with chlorine or hydrogen peroxides. But I think Ajinomoto Bio-Pharma is probably most known for its expertise in energetic reactions like azides, hydrazines, and to form heterocycles. And until a couple of years ago, we did everything in batch. So why go from batch to flow? I'm going quite rapidly over the benefits because it's already mentioned in the previous talk. So flow processing can really compete in batch with batch processing. And in recent years, we often do the exercise of translating processes from batch to flow because it helps us a lot in the fields that I mentioned before, mainly due to the improved mass and heat transfer. But also safety can be improved significantly. So in case of working with tubular reactors, there's no headspace, and also no explosive atmosphere can be formed over the reaction mixture, nor condensation of for example, shock-sensitive liquids like hydrozoic acid. Operating ranges over 150 degrees or over 10 bars are difficult to achieve in batch, while temperatures of over 300 degrees or more are possible in flow. Also, the use of alternative energy sources like light, electrons, or sound is also much more efficient in flow. Many of you have probably seen the huge boom in photo and electrochemistry articles recent years, and that's thanks to flow processing. Sorry. Unfortunately, I don't have the time to go over in detail of our flow chemistry capabilities, but we've implemented flow setups in lab, pilot, and commercial production, and some of them will pop up again in our case study. So I will go directly to our case study, and this one concerns the scale-up of a process involving the dangerous gas diazomethane and its toxic precursor for a cyclopropionation project for a customer. And this is on the picture how the project and its scale-up started in Belgium in batch. And it's important to have an idea on what happens. So the process requires 4 vessels with the first an addition reaction and also the second and the third additions. We are quite exothermic and they require very slow addition rates. Also because the intermediates that was formed here turned out to be very thermally labile with significant degradations even at room temperature. And the second and third addition here, they require dilution with a solvent for safety reasons, and the solvent is required as a heat sink. Without this solvent as a heat sink, a runaway was possible. And with the knowledge that the precursor that we're making in this one, that it can explode when it's heated above 150 degrees, you really want to avoid everything near 100 degrees already. And the final addition, these are used to have the in situ diazomethane generation and cyclopropionation. You could also notice that there are a lot of waste fractions that have to be dealt with. And for every truck of product, we have some serious amount of waste transports to be expected, especially if you know that we need more than 100 metric tons a year of this toxic diazomethane precursor. So I will directly go to the end, but I just want to say we succeeded in transforming the whole process in a much more sustainable process using flow, and we reached the targets that our customer wanted to have. But it was not easy to reach it, and it was also not realized in a few months. So I will explain in more detail what we needed to do. So the story starts in 2014 with a scale up towards the few tons of final products, the first few tons. And we started to notice in the lab to pilot scale up, it was not very evident. So we needed several iterations due to the thermally labile intermediates to have good conversions. But despite those difficulties in 2014, 2015, we managed in producing gradually larger amounts. So from 2 tons, 8 tons, and then 30 tons of this diazomethane precursor in batch. And also the subsequent steps at the same size. Due to the difficulties with the scale-up, the technical development, department started to look if we could use continuous flow processing, especially for the diazomethane precursor. Remember, we expected to make more than 100 metric tons, and this precursor synthesis in batch was becoming a bottleneck. And using the better mixing and heat exchange in tube reactors and the better heat exchange service, we thought we could do better in flow than in batch. We observed that only a few minutes of reaction time were necessary. So the first reaction was finished in less than 10 minutes, and the form intermediate didn't have to be stored at low temperature before starting the next addition. So it could be directly used after it was formed. That's a big benefit. And additionally, the second and the third additions only required a few seconds of residence times, followed by a short heating cycle in a coil reactor, sufficient for complete conversions towards the diazomethane precursor. For this realization, we had to change the chemistry a bit, using some different raw materials and also change direction conditions compared to batch. And that was thanks to the benefits of flow. So we could work safely close to the onset temperature of this diazomethane precursor, something that nobody wants to do in batch. We realized this proof of concepts in the lab with a total flow about 5 ml per minute. In 2014, we were still starting to design our flexible multi-purpose reactor for pilot flow processing. So starting from scratch, it took about 2 years for the IG Biopharma engineering and the tech development team to engineer and implement a plug-and-play setup in the pilot, so similar in flexibility and build-up as what Sebastian was talking about in this talk. In 2016, it was ready and tested. And this diazomethane precursor synthesis was the first commercial project we performed in the pilot. So in the summer of 2016, we made the first 50 kgs of good quality diazomethane precursor in the continuous flow pilot setup. And this was about 50 times the lab productivity. At that moment, workup was still performed in batch mode. We used tubular reactors for the first relatively slow step, so that's the 10 minutes that you have to take in mind, and a chemical silicon carbide reactor for the two fast exothermic reactions. After this successful pilot test, we started investigating and investing in continuous workup. So among the different extraction techniques that we tried, the countercurrent extraction column was identified as the best tool to recover lost, highly toxic diazomethane precursor from an acidic aqueous waste stream. This is how it looked like in our pilot setup. It was a very short or small countercurrent extraction column. So this is the smallest one that you can buy or rent from Sulzer. And the workup of this extraction column could be telescoped with a neutralization and removal of acidic traces in the product stream. And we performed that extraction in a simple air-cooled tubular reactor. The phase separation of the heavy and the light phase was performed in a homemade glass settler with an overflow glass. So very simple, very cheap system. In 2018, after the successful proof of concept of reaction and extraction, we started to design the commercial production plant and started requesting the permits and things like that. So this one was not a multi-purpose or nor a flexible production plant. It's really a dedicated plant that we need to build. So in 2020, this setup was ready, and the scale up to production of the diazomethane precursor in this dedicated setup was realized. So same as in pilots, we used tubular reactors for the relatively slow first step, and a larger chemical silicon carbide plate reactor for the very fast exothermic reactions. Acid wastes were extracted in a countercurrent extraction column, and while the neutralization, also mentioned in the pilot, was performed in tubular reactor and settlers, homemade settlers or homemade or designs, in-house designed settlers. The reaction and the workup in flow was performed at approximately 28 times the pilot scale. The part that I presented up to now, I call this phase 1. So it's really focused on the diazomethane precursor synthesis and the workup in flow. But still, we had these large waste streams. And also the IG Biopharma management asked quite soon, what about the batch cyclopropionation? Can't you do that also in flow? That would really be helpful. And the first thing I will do is what I call phase 2 and present this one. That was a really important phase because it handles the recovery, recycling, and of raw materials, which is a really big part of the cost of goods, of course, and also the costly waste treatments of the waste streams coming out of the flow reactor and the batch reactors, which are still used in the subsequent steps, the cyclopropionation. And thanks to the combination of thin film evaporation and fractional distillation of the organic product stream come out of the batch cyclopropionation, we could recover a very large part of the solvents and starting material A. So both items could be used in the synthesis of the diazomethane precursor and the subsequent workup. Simultaneously with the distillation work, we focused on the recovery of the precious metal. So we did that in using the know-how of a recent industrial collaboration project, an ICON project, as we call it in Belgium, funded by the Flemish government. And this was a collaboration between IG Biopharma, Inopsys, Janssen Pharma, and academic knowledge institutions. The outcome of that ICON project was a plant on a truck setup. And this setup treated the process streams with CO2 to lower the pH of this very caustic stream, which formed a bicarbonate waste stream where more than 75% of the palladium that we used as a catalyst could be recovered in an affordable way. This palladium comes back to us on a bank account, and the bicarbonate stream was treated to be used inside the workup of the diazomethane precursor. Another part was then the waste streams with a very highly toxic compound in it. Originally, all aqueous waste streams were collected, and every so many batches, we needed to treat them with very strong base to destroy the residual high toxic compound, the OEP5 compound. This meant a lot of strong base to be purchased, and it was at least 1 kilogram of base per kilogram of final product. So this means, in the meantime, we ramped up from 8 tons, thanks to flow, to more than 500 tons of active product per year. And unfortunately, this strong alkaline waste was not compatible with our wastewater treatment, and thus creating a large part of the waste transport again on the roads. And we found that the OEP5 waste, or the high toxic waste, could be thermally treated in a flow reactor at about 150 degrees at elevated pressure. So thanks to this thermal destruction with recovery of heat, I didn't mention this in this slide, we didn't need anymore this strong base, and we saved out also a batch vessel. This is a very simple coiled reactor, and we could use that batch vessel for further other projects. And because the waste was not so high in pH anymore, we can also treat it in our wastewater facilities. Then it's what I call phase 3. That's the third reaction in flow. That would really improve safety, because then we don't have to store a larger amount of inventory of precursor anymore. And it will also help in further cost reductions. But the third reaction, it was a multiphasic reaction. And it's the reaction with instituted diazomethane generation and consumption. So it creates a lot of nitrogen gas. A scale-up of those multiphasic systems is really difficult because mass transfer is key. It's not a problem if you have very fast reactions. You have plenty of different reactors available, but mass transfer from batch transfer in lab to pilot should be really equivalent or even better. And for this quite slow reaction, you need a lot of residence time. Actually, the mixing in the lab was not looking great if you cannot use high velocities or special reactor shapes. So we studied the scale-up of multiphasic systems first and quantified mass transfers in all kinds of reactors with rather long residence times. So we had in mind a residence time of up to 15 minutes for this kind of reaction. We managed to improve biphasic mixing in the tubular reactors using ultrasound, and that was just the first step. With a lot of efforts, we could get the same mass transfer or KLA values in pilot scale size tubular reactors with relatively short, very open setting mixers and a pulsator generating a pulsatile flow. This was also tested with the same standard biphasic hydrolysis reaction, allowing quantification of all the different reactors and comparison of the mixing. We were lucky that we were also generating the gas, and once it was generated, mixing also improves because you get more and more velocity in your reaction mixture. Using the learnings of the scale-up of multiphasic flow reactions, we applied it on the cyclopropionation step. And during the proof of concept in lab, we found that in flow, we had a much more selective reaction. The more selective reaction gave us the freedom to push the reaction conditions a bit more, and it gave us a result that was really highly appreciated by customer and management. So thanks to the improved selectivity, we don't have to use an excess of diazomethane precursor anymore. So we could cut 20% of this consumption. We could cut the expensive catalyst amount with a quarter. We could halven the amount of base that we needed for this cyclopropionation step, and halven the amount of solvent. Could work much more concentrated. There were 2 pilot campaigns with some iterations with the lab results. The first one, proof of concept in 2019. So can we do the scale up? And in 2021, after investing also in some CSTRs that were also mentioned here, we could optimize this reaction, that we had full conversion, no traces of diazomethane left over before the next downstream processing or the extraction started, and a very, very nice improvement in productivity. So the information gathered in 2021 is now being used in the design of a commercial scale setup. I'm already going to conclude this webinar. So yes, we could translate an originally 100% batch process to a partially flow process, improving the safety and the throughput. But over the years, we learned, when we learned about continuous flow, including the downstream processing and all the benefits of it, we could make a much better, bigger picture. So we transit so much more products in flow, more parts of it in flow, including the waste treatment. And a big part of this setup already has proven to work on production scale. And the others are at least proven on pilot scale. The benefits in the cost of goods, the environmental benefits, and the productivity are really looking great. Much more than just reaction in flow. The customers trust Ajinomoto Bio-Pharma also in realizing the setup for 100% in a commercial scale, and even ordered a second setup as a business contingency plan. And I would like to end my presentation by thanking a lot of people, so especially the people mentioned here that worked on the case study. And Christian mentioned also that the important collaboration that we need to have collaboration between technology development, the engineering, business, so in this case the flow business creation team, PAT, the process for good technologies, the pilot people, and process research and development, and of course many other internal partners. And finally, there were many partners involved in this project, but really a special thanks to Chemtrix, the Flemish government, Ajinomoto, AMS, Inopsys, and Manetco for this project, the case study. So I would like to thank you for your attention, and hopefully there are some questions.
Yes, thank you, Bert. It was an interesting talk, very interesting to see the plants growing larger and larger. And I personally like the plant on a truck. This has now really become reality. And it's good that you also take the trucks out of the road transport with the waste. That is really for the environment a very good action. Yes, we have questions. And before that, I'd like to mention that I overlooked one question from Doris to Sebastian. And Sebastian has kindly answered me over email, so I hope you can see it. I typed his answer in the Q&A chat. Now comes the question from Lucas. Great talk, Bert. I'm curious about the biphasic reaction through sonication. Do the phases separate again quickly after they pass through the sonication section, or do they remain relatively well mixed?
Oh no, they separate really fast again. So actually, you keep on seeing in these 1 millimeter bore tubing, you still see the slugs passing by, but the interfaces you are starting to see bubble flow, and that helps a lot. But after it comes out of the sonication bath again, it's really quickly separates again. So to get this kind of emulsions, you need higher speed, much more power of ultrasound, and probably a surfactant to get stabilization. But actually, for the downstream processing, you want to have separation as soon as possible again.
I have a question also to the multiphase reaction. It comes from Daniel. He says, for the multiphase reaction, was a phase transfer catalyst a major cost for the reaction when compared to other components such as solvent base and so on?
Sorry, was it about the phase transfer catalyst?
Yeah, if that was a major cost part compared to
major cost part, yeah. On the cost of goods, there's not a difference. So thanks to the multiphasic system, and doing it in flow, we had a lot of benefits on different parts. So we didn't have to introduce something extra chemically. We didn't have to do extra more energy into it or something like that. The biggest cost driver was productivity. So we needed really intimate mixing from the start, and avoid phase separation very, very fast. So we needed really to go to bubble flow before as soon as possible. And once the reaction started, as I mentioned, you have some gas generation, and then velocity is improved, and then also remixing is improved. But really initial mixing, that was the most important part on this biphasic system.
Okay, another question to sonication that seems to be interesting from Philip. Yeah, interesting also me the question. Did the sonication damage the reactor installations themselves?
Not in this lab scale-up or lab version. It doesn't matter. So we didn't see any problem, and also it's really just a simple cleaning sonication bath. It was nothing very, very strong, and this sonication is not used anymore in the pilot or in production. The moment it's just to get at least something better than the normal slug flow in the 1 millimeter bore tubing. And maybe to come back, you could also do this in microreactors, and then the mixing is much better. But once you go from a few hundred micrometers to 1 millimeter, yeah, you already lose a huge amount of the mixing efficiency. And then from 1 to 4, it's dramatic. So you go from 90% conversion or 90% to maybe 15% conversion, and that's really nothing anymore. So we really want to have that mixing equal between the 1 millimeter internal diameter, where we can make at least a few grams of product, and that pilot scale one.
Okay, I think we are perfectly in time. I don't see a new question anymore. I think we all deserve a pause from 20 minutes now exactly. And then we start with another session with 2 talks moderated by Tash Polios. And if you're in Europe, enjoy a coffee. In Australia, a tea or a wine. That's okay for the time of here. So enjoy it a bit and come back hopefully in 20 minutes. Yeah. Okay, see you then. 20 minutes silence.